Well,
Bam.
hello. Bam is right. That's it. Hello there, good friends out there in webinar land. John Barba here, along with Dave Holdorf. And thank you for joining us for another episode of Takeo Tuesday, our Tuesday training series that covers all topics, both commercial and residential. Today's topic is residentially focused, and we're going to talk about pipe sizing, air control, and this really crazy concept known as pumping away. Now, Dave, you talk to people all the time, as do I. Do we as an industry really have a handle on what pumping away is, do you think?
Well, it's been around for at least 25 years since a friend of ours wrote a book on it. Um, and it's still something that's still done today. I think it still comes to blows in some companies. I've worked with a few companies, installing firms, where it is split down the middle on and who's doing what, where they're putting the circulator on systems. So I love doing those training classes when I walk into a contractor shop and they're split down that way. Yeah. So it is still a conversation that goes on today.
And the interesting is, you said it goes back at least 25 years. It goes back almost 100 years.
Oh
It
yeah.
goes back into the 30s when Homer Thrush developed the first centrifugal pump, and put it on a system. Within about a month, they figured out where it should go. And there's early writings going back to the mid 30s on the point of no pressure change in pumping away. I think it was 1964 when Gil Carlson from Bell and Gossett wrote the seminal piece on, technical paper on the concept of the point of no pressure change and where the circulating pump should go. And then Dan Holohan in '90 wrote his book Pumping Away. We got to understand what we mean by pumping away. What are we pumping away from? Number one, we're going to get into that. And what happens if you don't? And a lot of what happens is going to depend on what kind of circulator you use, because we can't sit here and tell you all with a straight face, well, if you have the pump on the return side, the system won't work, because we have decades of evidence to prove otherwise. There are thousands, if not millions, of hydronic heating systems out there that have the circulator on the return that work just fine. So therefore, it can't be wrong, but can we be more right? So we're gonna examine all that and get into it in a little bit of detail, as well as talking about pipe sizing and air control as we lead up to pumping away. As we get started, we got a good group of folks out there. Could you do me a favor and go to the chat question section on your control panel and just chime in with your name and where you're from? I want to know. I want everybody representing. Where are we from, and what's it like out there? Gilles chimes in from Montreal. Bonjour, Gilles. Thank you. That's the extent of my French. And we got Branson from Oklahoma. Excellent. Welcome, welcome. Jose from Puerto Rico. Hola, thank you for joining us, Jose. And we got John from Norwalk, Connecticut, Joel from Manitoba, quite the international group. Tim from Fairbanks, good morning to you out in Fairbanks, Mississippi, Greensboro, British Columbia. Oh my goodness, we got a Philadelphia suburb chiming in, Steve from Delco. We have a New Jersey, so excellent. A lot of folks from all over the place. Thank you so much for being with us. We do appreciate it. Please do me a favor. Oh, go ahead, Dave.
I do want to state one thing. No, John and I are not being camera shy. Yes, we did shave. Yes, we are dressed and all, but cameras are not working today in the GoToWebinar platform. So that's why you do not see us this morning or this afternoon. So
Which may not be a bad thing, speaking
Yeah.
just generically. I've had a good look at the both of us today. You don't want to see us today.
I just figured I'd throw that out to everybody first.
There you go. There you go. So as we proceed, gentlemen and ladies out there, could you now that you know how to use the question chat section, and we get more folks chiming in. Terrific. Please ask your questions as they occur to you. Dave and I can talk all we want, but we're not that interesting. We really need you to kind of participate, and you'll do that by asking questions in this chat question function. And what we'll do is we'll just take a break every couple of slides and see if you have any questions that have popped up, and we'll address them as we go. I'm not a fan of waiting till the end for you to ask your questions, because most of the times when a presenter does that, they're just hoping you'll forget and he can skedaddle without having to take any questions. We don't particularly like that. So please ask your questions as they come up, and we will do our very best to answer them. We don't have all the answers, but between the two of us, we might be able to get most of them answered. So let's get the show on the road. Pipe sizing, air control, and pumping away. When we talk about all of these things. Well, let's talk about what we're going to cover today. What we're going to cover, of course, is finding flow so you can size your pipe. You can't size your pipe until you know the flow rate. So we're going to show you how to do the how to calculate the flow rate and then turn that into a pipe size. We're also going to talk, when we get into air control, we're going to talk about that magical 12 psi number. What's so special about 12 psi? And then from there, we'll talk about different air control options. You do have some choices when you're talking about an air separator or an air eliminator. They're slightly different. We're going to talk about both of those. And then we'll close the session with, hey, where does that circulator go? Does it go in the supply? Does it go in the turn? And what the heck does pumping away mean? And what are we pumping away from? So we're going to get into all of that today and hopefully answer as many of your questions as we can. So as we mentioned, it all starts with flow, all right? We can't do much in hydronics until we know what flow rate we're trying to deliver. Now, in order to find the flow rate that we're trying to deliver, we first have to know the BTUs that we're trying to deliver under design conditions. So it kind of goes back to a heat loss calculation. Now, we're not going to go through a heat loss calculation today, obviously, but to get a good idea of what the flow rate needs to be for a zone, for a system, etc., you need to have a clear idea of the BTU load of the zone or of the system. So because pipe sizing is going to be based on flow, flow is going to be based on heat load. To turn heat load into flow, we use an old friend. We call it the universal hydronics formula. Now, in our industry, people tend to be a little math phobic sometimes, not engineers so much, but us regular folk. This might be the only math formula that I think anyone in the trades needs to know by heart, because you use it to size pipe, you'll use it to size pumps, and you'll use it to troubleshoot. Other than that, it really has no purpose. I'd say those are three pretty important purposes. So yeah, it is the one thing that I think we need to know by heart. Fortunately, it is about as basic an algebraic formula as there is. And it states that GPM is equal to BTUH divided by the product of delta T times 500. GPM equals BTUH divided by delta T times 500. Let's define the terms. GPM, of course, stands for gallons per minute. That's the flow rate you need to deliver the BTUs required. So GPM is gallons per minute. BTUH, of course, is the heat load required under design conditions, right? So it's the worst case heat load under design conditions. That's what we're sizing for. Delta T is your designed for, keyword, designed for temperature drop across that piping circuit. Typically in residential hydronics, we will design to a delta T of 20, meaning the water might, in a high temperature system, the supply water goes out at 180. We're designing for it to come back at 160. That would make the average water temperature 170. Lower temperature hydronics, perhaps we have water going out at 130. We're designing for it to come back at 110. That would be an average water temperature of 120. All right. Residential radiant floor, we might design to a delta T of 10 in certain cases, between the floor joists specifically, where we want to try to average out and keep a more consistent floor surface temperature. So those systems might be designed to a delta T of 10. Now you putting radiant tubing in a concrete slab, a 4-inch concrete slab, okay, 15 or even 20 would be fine there. But those are the norms that we use. 20 degrees is kind of the standard. 20 degrees is what we'll use for our examples today. And then 500 is kind of a mathematical shortcut. It's a rule of thumb, if you will, for 100% water. Basically, that number comes from multiplying the weight of 1 gallon of water, 8.33 pounds. So we multiply 8.33 pounds times the number of minutes in an hour, that is traditionally 60 in most parts of the country, times the specific gravity of water, 100% water, has a specific gravity of 1, times the specific heat of the fluid, and 100% water has a specific heat of 1, because after all, it takes 1 BTU to raise 1 pound of water, 1 degree Fahrenheit in 1 hour. That's a lot of ones. We put them all together, 8.33 times 60 times 1 equals 499.8. Between friends, we'll call it 500, all right? Now that's 100% water at room temperature, okay? As the water temperature goes up, that number's going to fluctuate a little bit because the density of the water goes down. If you were to add glycol to the system. That's going to change. That 500 number is actually going to go down because it's heavier. The specific gravity is different. The specific heat is different. Okay, the only thing that stays the same is the 60. So the more glycol you put in, the lower that number gets. The lower that number gets, the higher the flow rate becomes that you will need to deliver the BTUs required. So let's say you put a 30% glycol solution into your system, that number might drop down to about 475 or thereabouts. You put a 50-50 glycol to water solution in for, like, say, a snowmelt system, that number might drop to 435. Okay, so you're going to need more flow. Then that's just a matter of how much glycol you put into the system. And we tend to over glycol things for residential applications that are not snow melting, obviously, but we tend to over glycol. But just understand, the more glycol you put in, it has an impact on flow, which has an impact on head loss through the piping, which has an impact on your circulator sizing. Alrighty, let's do a quick example, because again, this is pretty simple math. So GPM equals BTUH divided by delta T times 500. Let's say we're sizing a circulator for a single zone of whatever. Okay, well, it's panel radiators, it could be a single, series loop of baseboard. It's a zone. It's a zone, and that we are designing to a delta T of 20. And that zone has a BTU load of 25,000 BTUs, which makes it a pretty good size zone. So we fill in what we know. We know the BTUH is 25,000. We know the delta T is 20, and 500, of course, is 500. So we've plugged in what we know. Now we just got to do some math and figure out what it is we don't know. So 25,000 divided by 25 times 500. Well, 20 times 500 is easy. That's 10,000. And once you get to 10,000, you can divide anything by 10,000. It's one of the reasons we like using 20 as a standard delta T. 25,000 divided by 10,000 gives us a required flow rate under design conditions for this zone of 2.5 gallons per minute. So my circulator is going to have to be able to deliver 2.5 gallons per minute. And Dave, we've gone through this many, many times. Do we have circulators that can deliver that mighty amount of 2.5 gallons per minute?
Of course we do.
Yes, we have many. We have many.
Yeah.
In fact, one thing we don't have is we don't have a circulator that won't do 2.5 gallons per minute. So, so we got you covered there. We got you covered there. We'll
I
discuss.
thought it was a trick question there for a second. I was just like, wait, what?
Would I throw a trick question to you right out of the blue?
No, not at all. No, not at all.
No, you're right. I probably would.
Yeah,
I probably would.
I was paying attention because I usually zone out right about now. Yeah.
There you go. So 2.5 gallons per minute. Once we know the flow rate, now we can turn that into pipe size. And these are some very broad pipe sizing guidelines for you to use. All right. If my flow rate is 2 to 4 gallons per minute, 2 gallons per minute up to 4 gallons per minute. If I'm just talking about copper, type M copper, 3/4 inch pipe is fine. 3/4, that's your type M, type L, either one. 3/4 inch pipe for that 2 to 4 gallons per minute. So at 2.5 gallons per minute, bam, we're right there with 3/4 inch copper for that zone. If it's PEX, you'd want to look at the PEX manufacturer's guidelines, because a 3/4 inch PEX might have a smaller ID, thicker wall, smaller ID. There may be some differences there, and that'll help you figure out the head loss with that PEX as well. But we're looking at copper, 2.5 gallons a minute, bam, 3/4 inch, we're good to go. 4.1 up to 9 gallons a minute, we're looking at 1 inch copper. 1 inch copper between 4.1 and 9 gallons per minute. The reason these guidelines are the guidelines, folks, is we're trying to maintain a minimum and maximum fluid velocity. All right, a minimum of 2 feet per second and a maximum of 4 feet per second. Now, velocity, think of velocity as speed. Think of gallons per minute as volume. All right, think of that as volume. How many? It's like one car can go 70 miles an hour down the highway. If I got 40 cars nose to tail going 70 miles an hour down the highway, that's my gallons per minute, right? 70 miles an hour is my velocity. All these cars is my gallons per minute. So 4.1 to 9 gallons a minute, we're talking 1 inch copper. 8 to 14 is 1.25 inches. And there's a overlap there. We'll explain that in a second. And then up to 14, up to 22, we'll look at 1.5 inches and so on and so on. But why is there that overlap between 1 inch and 1.25 inches? 4 to 9 is 1 inch, 8 to 14 is 1.25 inches. That's kind of a little archaic overlap, but it's the difference between 1-inch type M or type L copper, and 1-inch Schedule 40 black iron. Now, they're both 1-inch pipe, but Schedule 40 black iron has a thicker wall and a smaller ID. To stay within those velocity guidelines that we just mentioned, with black iron pipe, yeah, you know what, you're going to want to stay at about 8 gallons per minute as your high end. With the copper, it's a thinner wall, bigger ID. You can go up to 9 gallons a minute with no velocity issues or concerns whatsoever. All right, folks, that's your basic pipe sizing. Pretty darn simple. Any questions that you have out there? How's the pace? Give me a little bit of feedback. How's the pace going? Is this making sense to you? Is this helpful? Give me a little bit of feedback into the questions section, and I'll know that A, you can hear me, and B, that we're reaching this. So if you could throw a couple of responses in there for me. Michael Clark says, good, okay, excellent. I'll take your word for it, Mike. Great, I appreciate that. Again, just keep giving us feedback, and your questions, of course, are always welcome. Boiler pipe sizing is a little bit different. Now, say we had a cast iron boiler, and the header coming out of that boiler needs to be sized to carry the BT load for the entire house, not just individual zones, but all the zones added together. Okay, so if I had my entire load was 75,000 BTUs at a 20-degree delta T, that'd be 7.5 gallons a minute. That would be a 1-inch header coming out of the boiler going to my zoning, and then I'd telescope it down from there. And by the same token, my return pipe would also have to be 1 inch. Now, condensing boilers, modulating condensing boilers are a little bit different in that they're a heck of a lot easier. The size of the pipe has not of the pipe connections, supply and return, as you can see in this chart, have nothing to do with load. It has everything to do with the boiler. In the manufacturer's instructions, they'll actually tell you what that is. So this particular model boiler, modulating condensing boiler, it'll tell you right there in the specifications. They 1 inch and a quarter pipe. All right, going from the boiler to the header and from the header back to the boiler. So that's your boiler piping would be 1 and a quarter inch in this example. So it's all about the header, as we show here. This is also one of the reasons why you will find many modulating condensing boiler companies now providing either a manufactured connection tailpiece like you see here. That's with the red and the blue valves there. That's a manufactured tailpiece that you buy, and it's made specifically for that boiler. Or they will provide low loss headers or a low loss header for you. So it just depends on what it is you're looking for and what it is you're trying to do. But all the answers can be found in the manual that comes free with every boiler. So there's your boiler pipe sizing in a nutshell. In this example, let's take another look at this. 127,000 BTUs for this modulating condensing boiler at a 20-degree delta T. That might be 12.7 GPM. Maybe we are looking at 1 and a quarter inch pipe there at that point. Very good, very good. Now, what's next in this whole piping scenario? All right, in this boiler piping extravaganza, we're going to look right down here. And if you can see my cursor right down here, we are looking at our air eliminator, our pressure reducing valve, and the expansion tank. Okay, those are kind of the first things you run into when you're piping up a boiler. The pressure reducing valve, if required by code, some places actually outlaw them, that you can't have them because they don't want the system connected to the plumbing system. It depends on where you are. Most places, a pressure reducing valve with an integral, in our case, with an integral backflow preventer, will take care of that for you. So pressure reducing valve, air eliminator, and expansion tank. That integral part that I was just telling you about is this guy, the Taco 3450 combi valve. This is a backflow preventer and pressure reducing valve in one unit, in one simple unit. That green kind of extension that you see there, that is part of your pressure reducing valve. And that black knob that you see at the end is actually a dial to help you set it. As with most pressure reducing valves, it comes out of the box set at that magical 12 PSI number, which we'll get to in a minute. But you'll also see that there's like a little gauge there. It's not really a gauge, because it doesn't tell you what the pressure is. You've got a pressure gauge for that on the boiler, but this will tell you what you've set it for. So if you're ever in that situation where, for whatever reason, you want to change the fill pressure in your boiler, Now you actually have something that tells you what you're setting it to, which makes life a heck of a lot easier rather than fiddling with this bolt and set screw and hoping you get it right. Here you have the ability to as you're adjusting, dial it into what you need to. That whole green and black piece is actually a separate piece that can be taken out, removed, cleaned if necessary. All right. Now this other section, the rear section with this little drain, that's your backflow preventer. Again, also serviceable. Just a neat, unique one-piece unit, one piece unit that does the jobs of two pieces. So just kind of something kind of cool that we've had out for a while that I wanted to share with you. Additionally, we also make boiler trim kits. They're not assembled. You have to assemble them, but we give you all the pieces that you might need to assemble them. And we give you three options. We give you an old style air separator, air scoop with an older style pressure reducing valve and backflow preventer. We give you the same thing, but with a 4900 high performance air eliminator. And then we give you the deluxe version, which has the high performance air eliminator and the 3400, but it includes the expansion tank, all the nipples, the shutoffs, everything you need to do, everything you need to, that you see right here, to build what you see right here. So just another thing that we have, a boiler trim kit to make life easy. Now, I promised you, why 12 PSI? Anybody out there know why we fill residential hydronic systems to 12 PSI? Any guesses out there? I know you know.
No, I got an interesting story for you. Yes.
Well, okay. Let's hear it.
It was actually the AHR show in 1948. A bunch of the manufacturers got together because everybody had their own valves and they all set them for different pressures. And they finally got together at the AHR show right before the show started, because you can't do it afterwards. And then decided to create that standard of 12 PSI because everybody's was different up to that point.
And we know why they chose 12 PSI, right?
Right.
Because it was practical.
And of course, that story I just made up completely just now.
Okay.
Sorry, I had to go there.
We'll remember this one in your yearly performance review.
Okay.
All right, Gilles, you want a job, man? I got you. Gilles actually got it right. Just to get positive pressure at the system's highest point. Yeah, it has to do with the static fill pressure of the system. We learned this day one, at least I learned this day one of plumbing school, and I went to go get my journeyman's license, and we had code school. A column of water 2.31 feet high, or 28 inches or 2.31 feet high, will have a gauge pressure at the bottom of 1 PSI. Doesn't matter how big or round it is, just how tall it is. So a column of water 28 inches high will have a gauge pressure at the bottom of 1 PSI. Stated another way, if I wanted to lift a column of water 28 inches up into the air, I would need 1 PSI to do that. Keep that in mind. So 1 PSI, 2.31 feet of water. All right. That's the gauge pressure at the bottom. Now let's look at this in terms of a structure, okay, of a structure. So here's a house. Looks like a 3-story house. So it's 5 feet. Let's say it's about 5 feet from the boiler fill level up to the bottom of the subfloor. All right. Then it's another 9 feet from there to the bottom of the subfloor of the second floor, and another 9 feet from there to the bottom of the subfloor, or to the top of the subfloor, to the floor level of the third floor. So that's 9 feet plus 9 feet is 18 feet plus 5 feet. That's 23 feet. Okay. Now, if I were to multiply, if I were to multiply, all right, 2.31 feet per PSI by 12 PSI. If you guys got a gonculator, go do that for you. Multiply 2.31 times 12, and you'll come up with 27.72. So 12 PSI is the pressure needed to raise a column of water 27.72 feet in the air. In this example, it's enough to fill and pressurize the pipe at the radiation level of the uppermost floor of a normal residential structure. All right. So that's why we use 12. If we have a taller structure, we might need to go with a little bit more. Okay, always keeping in mind that when that water is heated, the pressure will grow because the volume of water expands, the density goes down, the volume of water expands. We have to be cognizant of how high we raise that that static fill pressure within our system, because we're really worried about not 30 psi, the rating of the relief valve. We're worried about 27.5 psi, because that's when relief valves start to drip and weep. They'll open and blow at 30, but they'll start to drippy drip at about 27.5, and that's what we want to worry about. Okay, so that's why the 12. You have some leeway. Say you have a slightly taller run to the radiation level of the uppermost floor. Sure, you can bump that up to 15 psi. Absolutely can. But the important thing to remember is whatever you do to the pressure on the pressure reducing valve, you have to do the same thing to the fill pressure in the expansion tank. So say I'm going to turn my system up to 15 psi. I can do that, but before I put any water in the expansion tank, I have to charge the air side of that up to 15 psi as well. They have to be equal. They have to be about the same. Otherwise, your expansion tank is going to be too small. Basically, you're undersizing your expansion tank for the system, and you're going to approach that 27.5 psi a heck of a lot quicker. So those are the important things to remember. Whatever you do to the fill pressure, you got to do to the air side of the expansion tank, but you can't change the pressure on the air side of the expansion tank when there's water pressure on the water side. It actually has to be, you have to take that pressure off. Okay. Very good. Very good. All right. We're cruising right along here, man. Ready to talk about air elimination. Again, any questions you guys have on anything we've talked about so far, please just chime on in. But now we just want to talk about air eliminators. On the right of your screen, you see the good old-fashioned Takeo air scoop. And on the left-hand side, you see a modern high-performance air eliminator called the 4900. A lot of people look at the air scoop and say, why do you guys still sell that? Oh, God, that thing doesn't work. I beg to differ. I think it works, and it works really, really well if you know what it's supposed to do and if you install it properly. It's a nice, inexpensive air control device. All right, 4900 and its brethren, the Spirovent and others by Kalefi and Watts and whomever else, those things are designed to kill air dead. Okay, they're air eliminators. The air scoop is more of an air control device, but it's a very effective one, provided it's installed properly. Understand air control as a concept. Air, if you want to breathe, air's the best thing for you, right? But in a hydronic system, air is not your friend. Okay, air is bad on the inside of the pipe. Okay, air is really bad on the inside of the pipe. First off, it's an insulator. Okay, as we said earlier, the specific heat of water is 1. The specific heat of air is 0.24. That would be worse. Okay, that's not good. Air is an insulator, not a very good heat conductor or heat carrier, if you will. When you add air to this formula, air plus water plus ferrous metal, what does one get? It's in the vernacular, it's known as rust. Okay, and as we know from Neil Young, rust never sleeps. So yeah, we want that. Air's not our friend in that formula. And circulators really aren't very good at pumping air. They do a doggone good job pumping water, making water move, but they can't pump air. If you ever had a big old slug of air going through a circulator, you'll hear it go, "Rrr, rrr," it just doesn't like it. And in some cases, if you got an air bubble in the volute, okay, that circulator's airbound, and you got to make sure you come out and fix it, because the impeller isn't making anything go round and round at that point. So circulators can't pump air. Now, why do we remove air on the supply side of the system? Like coming out of the boiler, why do we put the air eliminator there? There's another question. If you're out there in the real world, shoot us what you think. Why do we have our air eliminator or air scoop, air control device on the supply side of the boiler? It's a good question. Let's see who's awake. First off, I know out in Fairbanks you're awake because it's bright and early there, right? It's about 6:30, 7:30 there. Jill's got it. Jill's on top of his game today. Yes, sir. Hottest fluid. Okay, that's where the water's the hottest. And if you've ever watched water boil, you know where we're going with this. The hotter the temperature of a fluid, the less capable that fluid is of holding dissolved gases in solution. Okay, when water gets hotter, the dissolved molecular oxygen wants to turn back into a bubble. Okay. So when you have your air letter outer located at the point in the system where the water's the hottest and the air wants to get out the mostest, we're working with nature rather than against nature. So that's again why we want to put this thing on the supply where the water is the hottest. So we're working, in harmony with Mother Nature. All right, very good. Good. Excellent, folks. Excellent. Real quick, the fundamentals of the air scoop. Now, if you look at this thing, it sure is shooting is telling you what to do, right? You've got this arrow. That's the direction of the flow. On one end, we put inlet. Thought about putting outlet on the other side, but with the arrow, thought that was a little bit insulting. So we didn't need to do that. And then you've got you like that one. Then you got your bell shape. Okay, the bell shape has to be pointing upward. Basically, when you're installing this, you want to be able to read the writing on that thing without contorting your body, without going upside down or going, don't turn it at a right angle. I've seen this thing needs to be installed horizontally with that high end upright, not down below. I've seen that thing upside down, and I've also seen it installed vertically. If you do it that way, what you've got is an expensive coupling rather than an inexpensive air eliminator or air separator. So it's not, it just doesn't work that way. So as long as you can read the writing without contorting your body, you're in very, very good shape. It's basic, it's simple, and what I really like about it, there's no moving parts. So there's nothing really to go wrong. There's nothing really to go wrong. What ultimately it is, it's super simple. It's a big open space in the piping. Now, remember when we talked about pipe sizing, our velocity guidelines were minimum of 2 feet per second, maximum of 4 feet per second. And at 2.5 gallons per minute, we chose 3/4 inch pipe. Now, I could certainly run 2.5 gallons a minute through 1.25 inch pipe if I wanted to, right? The circulator would barely feel any resistance at that point. I can get 2.5 gallons a minute through 1.25 inch pipe. I don't want to though, because the velocity is going to drop well below 4 feet per second. One of the reasons we have those velocity guidelines, the maximum is about 4 feet per second, is, and the minimum is 2 feet per second. If I exceed 4 feet per second, I'm going to get velocity noise and potentially cause erosion, internal erosion of the piping due to the high velocity. If my velocity goes below 2 feet per second, I get noise of a different kind. Dissolved gases at that low velocity tend to come out of solution as well, especially if they're hot. They'll come out of solution at velocities less than 2 feet per second. If you ever had like a zone of baseboard that sounds like a babbling brook, it might be a velocity issue, okay? We don't want that to happen until we do. In our distribution piping, we want a minimum of 2 feet per second. But once that water enters the air scoop, which is a big open space in the piping, the velocity goes down and then nature takes over. Air molecular oxygen starts to come out of solution, and it's walked into a trap, if you want to look at it that way. Okay, it's walked into a trap. There's internal veins in here that will literally scoop that out. Here's a little artist's rendition of what we just said. Okay, as the water enters the scoop, the increased, it's a big open space in the piping, slows the velocity. The dissolved gases want to turn back into bubbles. The turning vein, this little vein inside the air scoop, will literally scoop those bubbles up into the upper portion of the chamber, and they'll go out the quick vent. The key to making this work, ladies and gentlemen, is right there in the bottom right left of your screen. You must, in residential applications, have a minimum of 18 inches of straight, uninterrupted pipe going into the inlet side of this scoop. Think about what happens when the water comes out of a boiler, right? Water comes out of a boiler, hits an elbow, and the flow gets all turbulent, and the dissolved molecular oxygen gets all spread out through the entire cross section of, let's say, that 1.5 inch pipe. All right. I need 18 inches of straight, uninterrupted flow for the dissolved molecular oxygen in that water to work its way up towards the upper half or the upper portion of the pipe. It takes about 1.5 feet for that to happen, so that when it does enter the scoop and those things turn back into bubbles, the turning vane can actually do something with a big chunk of those bubbles. So you got to have that 1.5 feet. Now that said, has everyone here seen these things installed with oh, I don't know, a close nipple or a street 90 or just a small a short piece of pipe. At that point, it's a fancy coupling and a hanger for your expansion tank. That's all it is. At 18 inches, it'll do what you need it to do. Okay, it'll do what you need it to do. The challenge is, in most cases these days, we don't have that kind of room. More and more, I think, in modern North American hydronics, we're challenged with putting 10 pounds of hydronic, into a 5-pound closet. We might not have that kind of real estate. Okay, we might not have that kind of real estate. So if that is the case, then we have to change speeds here and go to a different type of air letter outer. In this case, an example would be the Taco 4900, which is a high performance air removal system that does not require a minimum pipe run. There's no minimum pipe run required for this unit. Okay, similar to the other high performance air removal items, no minimum pipe run is needed. It works in much the same way. It is a big open space in the piping, right? But once that water enters this big open space and the velocity slows down, instead of encountering a scoop, it encounters, in this case, a basket of these stainless steel computer designed three-dimensional Paul rings. These Paul rings act as a coalescence medium, meaning dissolved mini micro bubbles, little bubblets, tiny bubblets, all this kind of stuff will glom onto those Paul rings. And as more and more glom onto the Paul rings, the bubblets will get bigger and bigger and bigger, and then they'll go glug, glug, glug up into the upper portion of the air eliminator. And you'll see the water goes maybe 2/3 of the way up or half the way up in that upper portion. When more and more air gets into that upper portion, it'll eventually pull the float down, open the mechanism, and out she goes. Okay, it's a terrific little air eliminator that will eliminate air just as fast as you could pump it in. Actually, you do it faster, but there's no way to prove that. So it'll eliminate air as quickly as you can pump air into it. So an excellent solution to removal. In fact, independent studies have shown that this type of Paul ring technology will remove 3 times more and 3 times smaller mini micro bubbles than, say, the brush technology that you might find in a Spirovent or something else. And that's not the downgrade to Spirovent. Spirovent's a fantastic piece of equipment. It's just that we have 3 times more surface area of coalescence medium with those Paul rings than a Spirovent might have with its brush. So we can just remove 3 times more. It's just a math problem at that point. You have a very good piece of equipment versus a very good piece of equipment. So again, just understand the differences. Cool. All righty. Are we ready to talk about this whole pumping away thing? Let me check in with the audience here. How are you guys doing out there? Are we happy? Any questions that you might have? Or have we has all just this been preliminaries before we get to talking about pumping away? So give me a little bit of feedback. See how we're doing, what questions you might have, and just let me know, do you pump away or do you pump towards? That's a good question. What do you do when you're alone with just your conscience in the mechanical room? Do you put the pump on the supply or do you put the pump on the return? Dave, what do you do when you're all by yourself?
Oh, I always pump away.
Oh, I figured you would. Yeah.
Well, if I guess the answer to that question is more if it's new install, right?
Very good. That's what I was going for. Yep.
There are some good reasons for putting the pump on the return side. So, but we have to make sure we explore the right reasons on doing it.
Right. Yeah. If you walked into a job site, let's ask the audience out here. If you walked into a job site and there was a an old dead B&G 100, the big three-piece circulator, or a Taco 110, same thing, big old dead three-piece circulator, and that thing finally gave up the ghost and it needed to be replaced, and it was on the return side, what would you do? What would you do? What would be a good reason to put a pump on the return side? Asked Will Wilson. Well, let's talk about that. If you are replacing a circulator that's on the return side of the boiler, would you simply take that circulator out and put a new circulator in the same spot, or would you put it on the supply side? Knowing that putting it on the supply side is pretty much a repipe, okay? It's not a simple switch. It's pretty much a repipe. If that pump worked on the return side of that boiler for 40 years, I got a funny feeling if we put a similar circulator there, with similar performance characteristics on the return side, it's going to work for another 40 years. Okay. So I don't know if that answers your question, Will, but that would be a pretty good reason to have the pump on the return side because it was there already and worked fine. But as Dave said, if it is, if it's a new install or you're a boiler replacement, you're replacing the pumps and everything else, there's no reason not to pump away, none whatsoever. But let's talk about this. And what are we pumping away from? Well, we're pumping away from something called the point of no pressure change. I'm sorry, point of no pressure change. Jill says, check the NPSH. And NPSH is, if you're talking about commercial, yeah. These little residential circulators, NPSH doesn't really enter into it because it's so low. It's so low anyway. It's really not an issue. But you start getting into commercial pumps, NPSH and cavitation starts to become a real problem. So absolutely. Alrighty. So point of no pressure change. What is the point of no pressure change? There's another one for you. What is the point of no pressure change and why? Not only what is it, but why is it the point of no pressure change? Because I always thought if you're going to call something the point of no pressure change, doesn't it go to follow that if something's called the point of no pressure change, the pressure wouldn't change at the point of no pressure, right? That's kind of a reasonable expectation. If you're going to call something the point of no pressure change, well, the pressure shouldn't change there, right? Because it's called the point of no pressure change. That would be logical. However, I'm going to suggest to you that the pressure at the point of no pressure change does change, and it changes all the time. Because the point of no pressure change is where the expansion tank connects to the system. Usually, that's in conjunction with the air separator, okay, on the supply side. And that's really for convenience. Technically speaking, it could go anywhere in the system, all right, anywhere in the piping, as long as there's some place for water when it heats up to expand into, we're happy pilgrims, right? But from a convenience and service and everything else standpoint, it just makes sense. It's the easiest thing on the planet to put it right where the expansion tank, right where the air eliminator and pressure reducing valve come together, like we showed you in the boiler trim kit. That's the easiest place to put it. But why is it called the point of no pressure change if the pressure does change and it changes there all of the time? And here you can see a perfect example of the point of no pressure change. There you see the air scoop in conjunction with your pressure reducing valve backflow preventer pumping right into the point of no pressure change. That's the perfect place for your pressure reducing valve, by the way, because it's the point of no pressure change. It shouldn't change much to allow, it shouldn't go lower than what you set it at. That's kind of the key there. Now, in order to understand the point of no pressure change, let's understand how an expansion tank works, how a diaphragm tank works. When you take it out of the box, right? There's no water on the water side because it's just you're taking it out of the box. If you were to look down the little hole, you could stick your finger in it and you could push down against that diaphragm. Okay, it's all the way up towards the top. Then you fill it up. Okay, you fill it up with water and it's charged to 12 psi. You fill it up with 12 psi. You're at an equilibrium. The pressure on the water side is the same as the pressure on the air side, okay? Same as the pressure on the air side. The only way for the pressure at the point of no pressure change to go up, okay, would be to add more water to the tank, like so. And because it is an expansion tank, the only way to get more water into the tank is to heat the water up so it expands. Okay, and we're discounting leaks and valves and everything else. Just put that off to the side. That doesn't count for now. The only way for water to enter that tank to push that cushion down to increase the pressure at that point of no pressure change is for that water to be heated up. That's the only way it can happen. That's the only way it can happen. So the reason this thing is called the point of no pressure change is not because the pressure doesn't change there. It does. It changes all the time. And we're talking about Boyle's law here. The pressure does change and it changes all the time. The reason we call it the point of no pressure change is because it is the one point in the system, dear friends, where the circulator cannot change the pressure. The circulator cannot change the pressure. And notice I called it a circulator and not a pump, because they're different. A circulator circulates in a closed loop system. A pump pumps in an open loop system, right? So it's a circulator. Its job is to create, not to create pressure, but to create a pressure differential that will allow flow to ensue. High pressure will go to low pressure. So let's take a look at this. What can change the pressure at the point of no pressure change? We told you. You could heat up the water so it expands. The circulator can't do that. The boiler does that. The circulator can't do that. When the water heats up, the density goes down, the volume expands. It needs to go somewhere. It expands into the expansion tank. All right. Another way to change the pressure at the point of no pressure change would be to physically add or remove air from the tank. Now, the circulator certainly can't do that. It doesn't know how to use a Schrader valve. That's the biggest problem it has. You can't, it's hard to add air to the tank unless you have a compressor or something. Air can be lost from the air side of the tank just through the magic of oxygen diffusion. The manufacturers will tell you this, that rubber bladder isn't airtight, so to speak. Over the course of time, because we have high concentrations of oxygen molecules on the air side, low on the water side, you will actually get a little bit of diffusion, oxygen going through that bladder in a molecular state and getting into the system. And it's very, very slow, very, very deliberate. But the manufacturers say you might lose about up to 1 psi a year on the air side. That's why you want to have an isolation valve there so you can check the air pressure on that tank when you go in for a clean check and adjust every year. Circulator can't add or remove air from the tank, and the circulator cannot add or remove water from the tank. It can't do it because it's not a pump, it's a circulator. It's moving water, not pumping water. So the only way that would happen is if you physically opened a valve, whether it's a drain valve or the fill valve. That's the only way to add or remove water. Add or remove water from the tank would be to add or remove water from the system. All right. This still is kind of interesting. A lot of folks still have trouble with this, so I want to put it here visually. Here I have the circulator pumping into the point of no pressure change. So that's a circulator on the return side. That's the circulator on the return side. Now, let me grab a pen here. All right. So the circulator is pumpulating water that way. All right. Is there a situation, I would love to hear your input on this, folks. Is there a situation where that circulator could be so flippin' powerful that while it's doing its job pumping water through the system, it's going to just shove a little bit extra down into that expansion tank so it can increase the pressure right at that point? Give me a yay or a nay on that, folks. Can that happen? Is it conceivable that that circulator could be so monstrous that while it's pumping its gallons per minute through the pipe, it'll jam a little bit extra into that expansion tank and change the pressure at the point of no pressure change? What do you say? What do you say, folks? We got an answer from Jill. We got an answer from Will. I'm going to just, okay, let's say one more. Let's see, because I want to get a consensus here. Maybe, but I think no, says Steve. Well, let me ask you this. For those of you who said yes or are thinking yes, where would that water come from? Where would it come from? Because remember, we have a fixed amount of water in that system, correct? And it is a circulator, not a pump, okay? In order for that circulator to jam some extra water into that expansion tank, it would have to come from somewhere, okay? We've got X amount of water in the system. Where does it get the water, and what would it leave behind? And it can't be a vacuum because there's no air in the system. We can't create a vacuum unless we have air to begin with, right? So think about that. In order for that circulator to shove extra water in there and change the pressure at the point of no pressure change, it would have to pump water in there, and it can't because there's no water to be pumped. It cannot move water out of its circulation into that tank. Can't do it. Now, by the same token, if we were to pump away from that point of no pressure change, if we were to pump away from the point of no pressure change, could the opposite happen? Could this thing be so monstrous that by some crazy Venturi effect, we're taking water out of the expansion tank and shoving it into the system, thereby lowering the pressure at the point of no pressure change? Could that happen? Let's see what you say about that. I mean, could that thing literally suck water out of the expansion tank into the point of no pressure change? Is that a conceivable thing in your mind? We got a yes, and I hate to tell you, Odie, it's a no. because where would it put it? Remember, the piping system's already filled with water. In order to take water out of that tank and put it in the system, there needs to be space for it. There's no space for it, okay? It's already filled with water. So I can't, if I'm pumping towards the expansion tank, I can't shove any water in there because, where would it come from? And if I'm pumping away from the expansion tank, where would I put the water that's coming out of the expansion tank? So it's impossible. So that, friends, is why the point of no pressure change is called the point of no pressure change. It's not that the pressure doesn't change there. It can change there. The thing that's that changes it most commonly is the boiler. Boiler heats up the water. The water, the amount, the molecules get all crazy and move away from each other. The volume expands. Where does it expand? It expands into the expansion tank. That's its job. Otherwise, that's it. Circulator cannot add water to the expansion tank. It cannot remove water from the expansion tank. So as far as the circulator is concerned, the point where the expansion tank connects to the system is the point of no pressure change. What does that mean? Dave, what does that mean? Well, potentially nothing until we connect it to a system. So here we have.
Yep. I was muted. But
you
go
were
ahead.
muted.
Go. Yep.
You were muted.
Yes.
So here we have just a simple little zone, okay, going up to an air handler up on the second floor, high up on the second floor. And you can see from the expansion tank level to the top of the first floor is 5 feet. From the top of the first floor to the top of the second floor is 9 feet. And from the top of the second floor to that air handler is another 4.5 feet, okay, another 4.5 feet. So we add that together, it's 18.5 feet. So the highest point in the system is 18.5 feet above where my expansion tank is sitting. Now that expansion tank is charged to 12 PSI, okay? It's charged to 12 PSI as we would expect. Now, 18.5 feet above, we want to find out what the pressure differential is, the static pressure differential is between the expansion tank level and the water level way up high there, okay, at the highest point. Now that's 18.5 feet. To convert feet to PSI, we're simply going to divide by 2.31 because it's 1 PSI for every 2.31 feet. So 18 feet divided by 2.31 PSI per foot, the foots cancel out. I have an 8 PSI static pressure drop from the expansion tank level to my highest point. And that means with the circulator off and pressure gauges on the Gazinta and the Gazauta side of the circulator, both reading 12, because we're going to have it at the same level as the expansion tank in theory, my pressure at that highest point, if I had a gauge way up there, would be 4, because that's 8 PSI lower than my pressure at the expansion tank and circulator level. Does that make sense to everybody out there? And that's just static. Circulator's off. That's just the weight of the water, static difference, okay? So I've got 4 PSI up top, 12 PSI down at the bottom, and my circulator here is on the return side pumping towards the point of no pressure change. All right, let's turn this thing on. Let's turn this pump on. And let's say this circulator is capable of creating a 4 PSI pressure differential. Now, because I'm pumping into the point of no pressure change, that circulator's pressure differential cannot show up as an increase, okay? My outlet pressure can't change from 12 because I'm pumping into the point of no pressure change. That point of no pressure change is the pressure police. It says none, anything more than 12 PSI, none shall pass. All you get is 12. Now, the circulator's job isn't to create pressure, it's to create a pressure differential. It's doing its job if it has 12 PSI in the outlet and 8 on the inlet, okay? Because I'm pumping into the point of no pressure change, I can't raise the outlet, I drop the inlet, I'm doing my job. I've created that 4 PSI pressure differential. Now, in this case, remember, I've got an 8 PSI static pressure drop from the circulator expansion tank level up to that highest point in the system. At this point, that pressure at the highest point in the system would be about 0, okay? More or less 0. If I have 0 pressure, if I don't have pressure, I can't have a pressure differential. And if I don't have a pressure differential, I don't have flow. And if I don't have flow, I don't have heat. And if I don't have heat, I don't have a happy customer. If I don't have a happy customer, I don't have a happy life, okay? What winds up happening in this instance is the boiler's boilerating, the circulator's circulating, but the heater ain't heaterating, All right, it's running. It's you know, I feel heat, but I'm not getting flow. I have a flow problem, often misdiagnosed as an air problem, because you'll put your hand on the supply, it's hot. You put your hand on the return, it's cold. Oh, that's an air problem. I'll bleed this thing and get rid of the air. And you can bleed this thing until the cows come home. You're not going to solve the problem. You'll think you solved the problem, because the minute you turn that spigot on and bleed the loop, the water comes out cold, and pretty soon it's going to come out hot. By opening the spigot, you've created a pressure differential and have created flow. But we haven't really solved the problem, because the minute you shut it back, you shut off the purge, you close the purge valve and take the hose off, you have the same problem. Okay, we're not getting flow. It's a weird setup. Everything's working, but pressure is not working in our favor. So what do? I get a bigger pump, right? That pump ain't big enough. I better put a bigger one on there. So you say you put a circulator with an 8 psi pressure differential on there. You're not fixing the problem. You are, in fact, making it worse. You have no flow. You have no flow. The thing here, ladies and gentlemen, is this problem doesn't just occur over time. This happens when that circulator, remember I said about that old system with the B&G 100 or the Takeo 110 on the return side that worked great for decades. Pump died. We got to replace it. Okay. The problem is, if we replace it with the wrong pump, we're going to create this problem where there was none. Remember, the the Takeo 110, the B&G 100, high flow circulator. You do up to 30 gallons a minute, 300,000 BTUs, but it capped out about 5-6 feet ahead, because that's all it needed. All right, it was a low head pump, low pressure differential pump. At that point, it was a math issue. Low pressure differential pump worked just fine here. If this circulator was doing 2 psi worth of pressure differential, we're not having a conversation, right? We're getting heat. If I put in, let's say, a 3-speed circulator, your typical residential 3-speed circulator, Takeo 0015, Grundfos 1558, B&G NRF 22, the circulator, they all said, oh, it's the only pump you'll ever need. Keep it on the truck for service. It does everything. Nonsense. It doesn't. You put a high head pump like a simple 3-speed pump into that picture where a circulator used to work. Now you put in a high head 3-speed pump. Now you're creating a system where the system doesn't work. And that's a self-inflicted wound. That's not a problem with the circulator on the return. That's a problem with the wrong circulator on the return. If you took the wrong pump out and put the right pump in, which we call the hydronics hokey pokey, the system will work just fine. And that's what it's all about. Now, that said, so pump on the return, you got to replace it. Just make sure you replace it with the same basic performance characteristic circulator. If you're taking out a B&G 100, put in a low head pump. The Takeo 0010 3-speed was actually designed to be the replacement for the Takeo 110 or the B&G 100. You can set it down to low. It really emulates, low or even medium, it really emulates a high flow, low head, flat curve pump. Works perfectly in those situations. Now, if I were to pump away, different discussion, okay? Completely different discussion. So now I'm pumping away from the point of no pressure change. Everything's fine with the circulator off, but let's turn the circulator on, okay? Again, we have 4 psi up at the peak, but let's turn the circulator on, okay? 4 psi pressure differential. Now I'm pumping away from the point of no pressure change. Now I can add that circulator's pressure differential to my system. So my pressure on the outlet side will read 16 psi. And I go way up top, that'll be 8 psi, because it's an 8 psi static pressure drop way up there. So in this case, I always have flow. I'll also obliterate any air bubbles in the system. I'm not going to worry about that. I'm not going to have to bleed radiators or anything. I'll obliterate air bubbles, and it's always going to, I'm not going to have an issue with flow due to circulator location here. That's why we said, if you're building something new, hey, put that pump on the supply side, pump away from the point of no pressure change. That's a great way to go. Putting the pump on the return side is not wrong as a concept. It's the circulator you use there that might be wrong, okay? And typically your 3-speed circulators are probably the worst choice you could have for a circulator on the return side. In most cases, some cases there may be instances where they work just fine, and that's now that just becomes a math problem. But if you have that low head pump on there and you put a high head pump on there, and usually when you don't get flow, what do you do with a 3-speed circulator? You don't turn it down, you turn it up, right? And that's just making the problem worse. So in that instance, that would be the worst choice for a circulator on the return side. Circulator's on the return, replace it with something of similar performance characteristics. Could you move the could you say, you know what, I'm going to do it right. I'm going to move the circulator on the supply. That's not doing it right. That's repiping a job. All right. And then you have to explain to the homeowner why the system that worked this way perfectly for 40 years all of a sudden doesn't work anymore. Well, I got to move everything over here. That does not compute in the minds of any customer. Just make sure you know what you're holding in your hands for a circulator and why you're using it on this job, because another job might be different. That's one of the beauties of service, of understanding concepts and understanding system dynamics that can make you a great serviceman. All righty. Boy, Dave, that was fun, huh? And hey, all this has to do with Henry's law. If we understand Henry's law in terms of air control, the higher the pressure on a fluid, the more gas will stay dissolved in that fluid. All right. When you lower the pressure, vice versa, when you lower the pressure on a fluid, then those dissolved gases want to come out of solution. So if you think about it in those terms, pumping away helps keep air under control along with the air eliminator. So it's a great way to go. So again, if the pump's on the return, it's an old system, pump's on the return, no reason to move it. Just make sure you know what you're doing when you replace it. Building something new, replacing a boiler, doing a big overhaul. Yeah, pump away. It's easier that way. It's easier that way. Is that right? Okie dokie. And the else.
I want to add one. And John, I did put something into the chat. So if you want to see this in action, I built a display, which unfortunately is in Rhode Island at the moment, and I'm not. To show you how this actually works. All right. Yeah, we were showing you PowerPoint today and showing images and whatnot, but I included a link to a Takeo After Dark presentation that I had done a couple of years ago during lockdown, where I had that display that I had built here in the garage. And see it in operation. So you want to fast forward to the 1 hour, 15-minute mark. And that's when I zoom in on just that display itself. So take a look there and see it in action. So,
or you could watch the whole thing and just marvel at the splendor that was Dave, Rick, and I in during lockdown.
Yes, that too. Yes, I did notice in that video that was my my Ascot days. So that was
a day we're glad has seen its day. All righty, folks.
Yes.
And the other part of Henry's law, it has to do with water temperatures. Like as we said earlier, the colder liquid holds more gases. As liquid warms, the gas tends to come out of solution. So we got Henry's law, we got Boyle's law, we got all these kinds of laws. So that's all right. Good time for questions, folks. We do appreciate the gift of your time. Let me know, does this make sense? The way we explain it, does it make sense in a practical application, real world application? Because that's kind of what we strive for. And it's amazing. One of the more common questions our tech services people get has to do with a high head pump on the return side, that all of a sudden the system that worked great for 40 years doesn't work. And they say, there must be something wrong with your pump. I said, no, a pump's fine. It's just in the wrong place, or it's the wrong pump. So let's, it is one of the more common questions they get at tech services, which surprised me. But again, we look at you go to Facebook and the different hydronic heating groups. This pump away or pump, it always, someone asks, all right, final analysis, do we pump away on the pump on the return? And everybody's got an opinion, and it gets pretty heated. But to me, it's pretty simple. It both work. Just know what you're doing. They just know what you're doing. A lot of folks say, well, if the boiler companies didn't want you to have the pump on the return, why do they package the pumps on the return? Well, they used to, but they did it for a really good reason, and had nothing to do with boiler performance. For the longest time, it had to do with simply shipping and crating. It made it easier to crate up a boiler with the pump packaged on the return, and made it easier to ship without damage. People will always say, well, they do it that way because the seals on those pumps can't handle the high temperatures on the supply. Hey, 1957 called it wants its hot take back. Okay, that hasn't been an issue since the late 50s, early 60s. It was an issue in the 40s, and that's why because the pumps used to be on the supply, they leaked like crazy. Let's move them on a return where the water's cooler. That was a 1940s solution to a 1940s problem. We have materials now that can handle anything a hydronic system can throw at it. So temperature isn't the issue. It's habit and just kind of understanding system dynamics. So. Excellent. Excellent. Dave, anything to add, my friend?
No, man. I think this was an excellent class today. Again, one of those things that we may take for granted, but now we understand where it comes from and why we do what we do. Um, and when you start talking about the math part earlier, when we are doing pipe sizing and delta T's, that is a lot of the magic behind it, so to speak. And I hate to say the word magic, but
Yeah.
you can use that calculations, those numbers back there, to work a system in your favor. So I know when John was talking about those pre-piped headers that come with some of the boilers, a lot of times they're going to be piped in 1 inch, but the boiler might be 150,000 BTU. So if you use the default number of 20-degree delta, that says no, this should be 100 and I should do inch and a quarter, inch and a half pipe here. But the boiler manufacturers are working with a delta T of 30 to 35. So when you change that delta, that's when you get a smaller pipe size. You don't need to do the same flow rate. So bigger pipe doesn't get you more except for spending more money,
There
right?
you go.
So you can work with those numbers and make it work to your advantage, so to speak.
Very good. Very good. One last call for questions. Anybody out there? Let us know. How was this session? Was this session helpful to you? Did you enjoy it? Was it stuff you could use? So give us a little feedback before we sign off. Just want to hear from you and make sure we did right by you today, because we put a lot of work into these things. We want to make sure we get you the information that you're looking for and that is helpful. So let us know if we succeeded. If we didn't, well, we want to know that too. Oh,
And
we got a good job from Chris. So I'm going to take that as gospel. How about you, Dave?
yes, perfect. Yes, and hang up quickly. In 23 hours time, you guys will see an email from us. One, thanks for joining us for another edition of Takeo Tuesday, as well as a link to this recording, so you get to watch it again if you really liked it.
And again
And
and again and again too. I mean, if
share
you
with your
really,
friends,
really.
as well as your certificate of your PDH will also be there as well.
Coolness. All right, folks. Well, hey, thank you so much for joining us on this beautiful Tuesday. I hope it's a beautiful Tuesday where it's a hot Tuesday up here today. But thank you for joining us on this wonderful Tuesday midday extravaganza. Tomorrow night, just a quick note, quick programming note. Write this down, people. Write this down. Tomorrow night, 7 p.m. Eastern Time, Takeo After Dark rides again in our new format, in our new way of absorbing this, of using this. We'll have you can still join this on GoToWebinar. You can register for it. Go on GoToWebinar and watch it that way. We will also be simulcasting. We're going to be streaming on multiple platforms. Let's put it that way. We're going to be on Facebook Live on Takeo's page on Facebook Live. We're going to be on YouTube Live on Takeo's page. We're going to be on LinkedIn Live, also on Takeo's page. And are we getting Instagram this week or not, Dave? Do you know? Are we giving that one a shot?
Not yet. We're still trying to figure out the LinkedIn issue.
Still trying to figure that.
Yeah.
Yeah, this is like our third preseason game on our new format. So please be on the lookout for that. You don't have to register for any of that. Just check in get yourself an alert from YouTube or from LinkedIn or from Facebook, and you can and just make it a point to be there. It's going to be interesting. We're going to be talking about domestic hot water recirculation. Sizing for that and what happens if you oversize. We're going to be doing a little bit of pics from the field, showing some different job sites that people have sent us pictures about. And Dave and I will be sharing our insights on all things about hydronics and plumbing and life in general. Right, Dave?
That's right. Of course. Life in general. Yes.
Life in general, because Dave has a lot of wisdom. I like to think I have a lot of wisdom. Together, we're incredibly wisdomous. And we will be sharing that with you tomorrow on Takeo After Dark, 7 p.m. Eastern Time. And you'll be able to chat with us and ask questions and make comments on all of those platforms. It's going to be kind of exciting. So we hope we see you all there tomorrow night.
Excellent, everybody. Thanks
with that.
I guess we'll sign off on that.
All righty. With that, we'll say thank you much, and we'll see you next time on Takeo Tuesday. Ciao, everybody.